NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Well, JWST is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful.
Pluto, a faraway and confounding, more modest planet, was once a singular member of our planetary family. However, later disturbing statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with a shocking revelation. They propose that this cold world is on a potential collision course with Neptune. Yet how could this happen, and what might be the consequences of such a significant event? Are we witnessing an intriguing cosmic phenomenon, or is there something else to this impending celestial accident? Join us as we explore the potential outcomes of a Pluto-Neptune crash. Pluto, a former planet that was downgraded to a dwarf planet partly due to its curious orbit, remains a subject of interest and study in the astronomical community. According to recent predictions by leading researchers, Pluto's trajectory is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially hazardous collision between these two celestial bodies, which could pose a massive threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. Takes an astonishing 248 years to complete a single orbit. This means that since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating entirely from the nearly circular orbits of the major planets. What makes Pluto's orbit even more extraordinary is its inclination, measured at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to the other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune's. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to grasp its unique trajectory. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and eccentric shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of celestial mechanics. The three-body problem in space involves understanding how three objects like Pluto, Neptune, and the Sun move and interact with each other through their gravitational pull. It's akin to predicting where they will go based on where they start and how they affect one another. For Pluto, this issue highlights how its path, Neptune's path, and the Sun's gravity all interact in a complex manner. Terms like asymptotic libration and apsidal libration, along with the VSK oscillation, are key to this puzzle. According to astrophysicists, what keeps all planets in their orbits is a kind of libration. In Pluto and Neptune's case, this term means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from colliding. Degree libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an additional layer of protection from potential impacts. Another critical factor in this situation is the VSK oscillation, named after three researchers, Vov, Macaulay, and Kai, who studied the motion of objects in space. It examines how three space objects like Pluto, Neptune, and the Sun interact through their gravitational pull. This interaction influences how they move. In Pluto's case, the VSK oscillation helps explain why its orbit around the Sun is so unusual. Despite the apparent chaos, this oscillation helps keep Pluto's orbit stable for remarkably long periods. The VSK oscillation demonstrates that even though things in space may seem wild and random, certain patterns and rules maintain order. These factors help stabilize Pluto's orbit, ensuring it doesn't collide with Neptune or veer off course. The three-body problem explains how these orbits change due to the gravitational pulls of celestial objects. Studying this helps us learn more about Pluto, our solar system, and distant stars and planets. Mathematical simulations in the late 1980s revealed that despite these stabilizing properties, Pluto's orbit is inherently chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unusual properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively containing the chaos. Recent computer models have shown how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only planet contributing. Jupiter's gravity also plays a significant role in protecting Pluto's orbit, and Saturn helps as well. These models show that Jupiter's gravity alone is strong enough to keep Pluto on a steady path for an extended period, possibly even billions of years. Perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely in space without encountering trouble. These dynamics are vital in the broader context of the universe for maintaining the order and consistency of celestial motion. Without these factors, the solar system as we know it would be a place of far greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable orbits, triggering a domino effect on other celestial objects. For Pluto, especially with discussions about it potentially colliding with Neptune in the future, understanding its orbit is crucial. This provides us with a clearer picture of the solar system's dynamic nature. Pluto's case illustrates how even the most seemingly unstable orbits can achieve a state of balance through the intricate interplay of gravitational forces and orbital mechanics. It also underscores the importance of continuous observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in Pluto's case. This means that even slight variations in Pluto's position or velocity can significantly alter its long-term trajectory. Using computer simulations has been immensely helpful for researchers in understanding how Pluto moves in space. These simulations employ intricate mathematics to model how Pluto and other space objects like Neptune interact gravitationally. By adjusting small details in the simulations, astronomers can see how tiny here Pluto ends up. Distinction in where Pluto is or the way in which quickly it's moving over numerous years, its path can end up looking totally different. Anyway, in spite of this chaos, Pluto's orbit remains stable for quite a long time, billions of years. This implies Pluto's journey around the Sun has a sort of order to it, even though it initially seems chaotic. Predicting major events, particularly when they involve chaotic orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainties. While mathematical simulations provide a strong foundation for understanding and predicting the future behavior of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, The chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made tremendous strides in understanding space, the case of Pluto reminds us how our knowledge of the cosmos remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can have sweeping effects, influencing the stability and trajectory of other bodies within the system. So, why are prominent astrophysicists only now raising concerns about a potential collision between Pluto and Neptune? Despite the complex forces working to prevent such an event, Neil deGrasse Tyson, a renowned astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in the reclassification of Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unexplored realms of space. Tyson's stance on Pluto's reclassification is rooted in the ever-expanding knowledge of our solar system. He views the reclassification not as a demotion but as a necessary adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of Pluto's orbit and its interactions with Neptune through a lens that recognizes the unpredictability of space. He suggests that while Pluto's orbit is stable for now, it could undergo significant changes in the future. This makes studying its trajectory particularly important for understanding the broader forces at play in our solar system. As Tyson often notes, science is ever-evolving, and Pluto is a prime example of how new knowledge can reshape our perspective of the universe. Tyson's concerns about Pluto's long-term stability stem from the ever-changing dynamics of our solar system. Despite its current stability, Tyson acknowledges that future shifts in the gravitational interactions between Pluto, Neptune, and the Sun could lead to unexpected changes. The delicate balance that currently keeps Pluto's orbit stable may eventually be disrupted by changes in the Sun's gravitational influence, the movement of other planets, or even the impact of new forces yet to be discovered. Tyson's emphasis on these future uncertainties serves as a reminder that the universe is a constantly shifting system, and that even what seems stable today could change in unforeseen ways. His warning about the possibility of a collision between Pluto and Neptune highlights the evolving nature of our understanding of celestial mechanics. As we continue to study Pluto and its peculiar orbit, we must consider how the forces of gravity and the intricate interactions between celestial bodies will continue to shape the future of our solar system. The potential for a Pluto-Neptune collision might be a distant possibility, but it underscores the importance of ongoing research and the need to continually adapt our understanding of the universe as new discoveries are made. Ultimately, our understanding of space, time, and gravity will continue to evolve, revealing ever more astonishing phenomena. This is the journey that awaits us as we look to the stars for answers to questions that have long intrigued us. Pluto's future may seem uncertain, but with each new study, we uncover more about how our solar system operates. The cosmic dance of planets like Neptune and Pluto reminds us of the immense complexity and grandeur of the universe. While it is clear that Pluto's orbit is likely to remain stable for the foreseeable future, the potential for change is always present, hidden within the chaotic nature of space. Pluto's journey through space, despite its current stability, is far from simple. As a dwarf planet, it provides a unique case study of the intricacies of celestial mechanics and the forces that govern the solar system. The fact that its orbit intersects with Neptune's without leading to a catastrophic collision challenges conventional expectations. This fascinating scenario invites further exploration of how various forces work together to prevent objects in space from colliding. While Neptune's gravity is often considered a dominant factor in shaping Pluto's orbit, the interactions between all of the solar system's planets, especially the gas giants, are crucial in stabilizing Pluto's path. Jupiter, with its massive size, plays a key role in this gravitational dance, helping maintain the balance of the smaller, more erratic bodies in the outer reaches of the solar system. Saturn, too, with its immense rings and gravitational pull, contributes to the overall stability of planetary orbits. These giant planets act as cosmic shepherds, ensuring that Pluto's orbit, despite its eccentricities, remains largely free of danger. In addition to gravitational influences from other planets, the Sun's gravity remains the ultimate force shaping the trajectories of every object in the solar system, including Pluto and Neptune. The Sun's pull is responsible for the overall pattern of orbits and the underlying stability of the solar system. However, the Sun itself is not static. It undergoes various cycles of activity, including solar flares and changes in its magnetic field, which may, over incredibly long periods, subtly affect the orbits of distant bodies like Pluto. These changes, while minor over short periods, could potentially alter how Pluto and Neptune interact in the distant future. The study of Pluto's orbit not only provides insight into the past and present states of our solar system but also sheds light on how planetary systems evolve over time. Although Pluto is currently safe from a direct collision with Neptune, the dynamic nature of the solar system means that no orbit is truly fixed forever. There are forces beyond gravity that influence the movement of celestial bodies. Even the smallest disturbances in the orbits of planets can lead to larger shifts down the line. This chaotic motion is one of the fundamental characteristics of the universe, constantly shifting and evolving, presenting new mysteries for astronomers to unravel. The anticipation of a potential Pluto-Neptune collision in the future, though highly unlikely in the short term, highlights how even stable systems can be unpredictable over long timescales. By modeling the orbits of objects like Pluto, scientists not only understand the current configuration of the solar system but also gain valuable insights into the mechanisms that could shape its future. Simulations of Pluto's orbit have shown that its path around the Sun is sensitive to small changes in initial conditions. These minor adjustments, when amplified over millions or even billions of years, could ultimately lead to significant changes in its orbit, potentially bringing it closer to Neptune's path. Furthermore, the ongoing study of Pluto's orbit raises the question of whether other dwarf planets or trans-Neptunian objects may one day experience similar encounters with Neptune or other larger planets. The outer solar system remains a realm of great mystery, with many objects yet to be fully studied. The dynamic interactions between these bodies could reveal more about the mechanisms that govern orbital stability and the eventual fate of the solar system. Ultimately, the future of Pluto and of the rest of the solar system will depend on a combination of forces: gravitational, physical, and perhaps unknown factors that scientists are still striving to fully understand. The complexities of planetary motion offer a glimpse into the long-term future of the solar system, where even seemingly stable systems are always subject to change.